So ठीक है. I hope कि ये जो भी participant है, because FDP मतलब तो faculty development है. So they are faculty members in other institutions.
Mostly faculty members and some are PhD students.
Okay. हाँ ठीक है. Both are in the same category. So
Yes,
thank you very much, Professor Sanjeev and Dr. Shailendra. It's nice. It's nice to continue with what I was just sharing my ideas during inaugural session. Any question to anybody, you can always interrupt me in the middle, and I will be happy to clarify within my limits. So let me continue with my topic, what I have chosen today: power electronics interface for energy storage and renewable sources. So as you all know that neither renewable nor storage is nothing new actually, right? I hope you agree. For about more than 100 years, these wind turbines are there. They may be used for, they might have been used for lifting the water. Then there are a lot of ways to harness the solar energy is also there, which is used to heat up the water or some other form of energy. So renewable in its core form, in its original form, is nothing new. Similarly, as far as storage is concerned, you know, storage is there forever. I mean, for centuries, people used to store the water. People used to store so many other things for future use. But definitely, use of these technologies for electrical purpose is something which started by last century. We started with the wind turbines for generation of electrical power. We started with solar photovoltaic for generation of electrical output. This is definitely new, comparatively new, as far as general storage and as far as general renewable is concerned. Now, processing electrical power is something which requires some media, some equipment or some media, right? Because conventional electrical power, if you all know, is like a synchronous generator, which is converting a fuel power, like power from the fuel into the electrical outputs in a gigawatt levels. That's what we are familiar. But what is something which is very exciting is that we need to use the devices for power conditioning, right? So over 20-30 years, we are working in this area. Almost started by 2000 this year, so almost it is 22 years for me to work in this area. That how can we condition a power? How can we condition a electrical power? Not any power, electrical power. So initially, in the first decade of this century, 2000 to 2010, people were very keen to compensate the power in a distribution and transmission system. So comes the fax devices and then the custom power devices. So initially, we also worked in these areas, conditioning of power in a distribution, transmission, and even at a higher generation level as well. But later decade of this century, after 2010 especially, the requirement came down to actually transfer the real power from renewable. That was 2010 to 2020 almost. And now this decade, just I was mentioning in my inaugural speech, 2020 to 2030 will be the decade of power transfer and storage in a electrical storage or electrochemical storage. So ultimately, doing all these jobs is done by some static devices. And what is all those static devices? Is best is a power electronics converters. So power electronics converter is actually a solid state or the static way of conditioning or transferring a power. That's all we wanted to. I just wanted to emphasize on this point. So that's why I chosen this power electronics interface for renewable and storage. So as you all know, energy is a major input for overall socio-economic development of any society. Uh, I mean, the status of any country or the is depends upon per capita utilization of electrical power, right? That's what indicates how developed the country is. So you will be surprised to know that US and China are about 4 to 5 times higher per capita energy utilization, right? So that's why they are more developed as compared to our country. So somehow or other way, we have to increase per capita utilization of energy. So that's what is the indicator. Energy is a major input for overall socio-economic development of any society. Global electrical energy demand is steadily rising, and consequently there is a demand to increase the power generation capacity. So the same thing, the prices of fossil fuel steeply increasing and increasing pollution. These all are well known. Renewable sources of energy is expected to play a key role, and significant percentage of required energy can be based on renewable and data. So as far as renewable is concerned, as you all know, that government has set a target of 175 gigawatt through renewable out of this complete model of, let's say, 500 gigawatt. 175 gigawatt should be from renewable. And out of that, 100 gigawatt should be from solar and 60 gigawatt from the wind turbine. Now, this target, 175 gigawatt, you can see right now we are at 114 gigawatt. So it is supposed to be met out by this March, but it has been extended till 31st December. So this data is going to be changed very significantly by the end of this year, and this will become 175 gigawatt, and will stand approx 35% of our total installed capacity. But I mean, this is something. I mean, you can say we are standing about 30% of renewable at the moment. But there is other side of this data also. Always remember that this installed capacity is a power capacity, right? And you must be understanding the difference between the power and the energy. So if you compare energy, especially the energy part, you will see that the net yield of energy is still only about 6 to 8%. As far as solar is concerned, we just have only 4% of energy contribution in our utilization from the solar. So maybe we have about 15% of solar at the moment. At the moment, we have 15% of solar in terms of installed capacity. But in terms of energy yield, it is only 4%. So why this difference? This difference is because average operating hour, or we call peak sun hour, for solar is only 5 hours per day. Okay, whereas average operating hour for any thermal could be even 24 hours, or in general it could be 20 hours. So that's what the difference. So we are talking so much of renewable. That's very correct, very timely, and important also. But we should always keep in mind that net yield of the energy is only 6 to 8% from renewable and 4% from the solar. That was only my submission at this stage. You should know, as an electrical engineer, you should know about this fact. Okay, this is a global scenario. Everywhere, in every country, there is a talk of renewable. So we can see that there is a steady growth of solar and wind power. You can see 26% is the share of solar in overall global power, and 26% wind. In terms of renewable energy and 43% hydroelectric. In most of the countries globally, renewable also include hydroelectric. But in our country, hydroelectric, anything more than 25 megawatt is considered to be less than, more than 25 gigawatt is considered separately in a hydropower planning model. But in globally, renewable include hydro also. So still, we have one of the major hydro renewable power. But again, 26% is share of solar and wind. Most of the countries like US and Europe, they rely mostly on the wind, whereas Asian countries, we mostly rely on the solar, because the very simple reason, we have a pretty uniform condition of the solar throughout the year, throughout the day. As we all know, Central India, sitting in the Central India, we about have 10 to 12 hours of sunshine hours, mostly 8 to 12 throughout the year, maybe 8 hours in winters and 12 hours in the summers. So that's what the situation in our Asian countries. Some of the information I would just like to share to all of you, which may be useful and which may be important to all of you. The battery energy storage will be included in planning model from year 27-28. Right? What is the meaning of this? Meaning of this, as per Central Electricity Authority, battery energy storage capacity of 2700 megawatt means about 27 gigawatt, which is the part of this pie chart. That's what the meaning is. As you can see, 114 gigawatt from renewable. You will see another triangle which will be indicating 27 gigawatt from storage. By which year? By 29-30, means by the end of this decade. And the country will have a national storage of about 108,000 megawatt hour. That is approximately 27 gigawatt of power can be injected in the grid for about 4 hours. Right? So you can think of such a huge potential of storage by this decade. So that's why I mentioned that this decade will be dedicated for the storage. And now the problem is not a storage. Okay, storage is there is some different groups which are working in a development of storage. They are basically the chemical or material engineers who are developing the new technologies like lithium iron phosphate, which is able to generate, I just given 2800 kilowatt hour in a single enclosures. They are the different group. Our group means we are electrical people. Our task is to process this huge power. This is our task. Because generating energy or power is one thing, but processing that energy or power in a grid scenario is a very different thing. So that requirement has to be filled up by the group like us, like electrical group, power electronic group, power system group. These are the group which is actually responsible for processing such a huge power. And another important thing about the storage is, like renewable is a unidirectional power flow. You need to design a converter which will transfer the power from solar PV plant to the grid. But as far as storage is concerned, you should have a bidirectional power flow, because not only you have to retrieve the power, but you should have a storage of the power on the same line. So the power will be both way, bidirectional, and you should have a very good round trip efficiency, right? I hope you understand the round trip efficiency, the ratio of the power retrieved to the power stored, right? So those definitions are always there. Another important information which supports the solar actually is EVs could account for 43% of total electric vehicle sales by 2030. So this is another segment of medium power range, which says that according to Center for Energy Finance, uh, EV sales, battery requirements, public charging infrastructure, and necessary other investment needed until 2030 to support India's EV transition. So that's another feather for this uh, decade. That and we are all feeling the heat of this electric vehicle. Everybody is writing project, everybody is publishing paper, everybody is doing research. Right. Now, third information, I'm just picking out some information and sharing with you all. India needs to generate 83% of electricity from renewable energy to achieve net carbon emission by net zero carbon emission by 2050. This is according to Council on Energy, Environment and Water. This is just data that if you want to achieve net zero carbon emission by 2050, you have to generate electrical power from renewable, 83% of electrical power. And then recently last year, in the COP26 meeting, India has pledged to achieve net carbon emission by 2070. So ultimately, we have to achieve this net carbon zero emission by 2070, by whatever means. And other side, I was talking to NTPC people, they are saying that they have got a target 2030 to achieve net carbon emission. So net zero carbon emission by 2030. So I was just asking them that how will you actually achieve this net zero carbon emission by 2030? Whereas 60% of the power generation is still from the thermal resources in our country. And 65% of the energy is still from the thermal power. So how will you actually achieve the net zero carbon? So they said, no, it doesn't mean that we shut down all our thermal power plants. It only means that we are replacing existing thermal power plants by supercritical thermal power plants, which has much higher efficiency as compared to our older thermal power plants. This is one way. We have to quench the carbon emission mechanically by other way. And then we have to compulsorily install 10 to 20% of renewable if we have to run our plants. So these are the ways to achieve net zero carbon emission given target to especially the thermal power agencies. So, and another information again in the last year COP26 meeting, there is an idea of one sun, one world, one grid, and it aims to harness solar energy wherever the sun is shining at a global level, and almost 2600 gigawatt of interconnection may be possible by 2050. So that's what one of the very high profile targets this COP26 also set up, that how can we harness the solar power, because sun is always there in the earth. It may be in one or other part. It is only the matter of that in which part of the country we harness the solar power, and if we have a single corridor or global corridor, it may be possible to even transfer that part of the power. So these are some of the just basic information which supports the renewable and energy storage technology. Okay, this is one bar chart which say the status of renewable. So of course, the China is one of the leading country in the term of both generation, consumption, and manufacturing of solar power. This renewable power. Then the US with 264, and then India, of course, with 128 gigawatt of. But this data is up to 2019. But it's giving a fair idea that we have to still achieve lot of things over the coming years to compete with the globally, right? This is one of the renewable energy map. You can just type this this URL on your Google, and you will be able to locate the status of renewable current status and the past status. So that's a very useful way of looking upon the status of renewable energy over the whole global scenario. Now, there are a lot of challenges apart from injecting real power into the grid. As far as power electronics and power system point of view, there are a lot of challenges arising out of high penetration of renewable and storage into the grid. Those are like power quality, reliability, safety and protection, load management, grid interconnection, new regulation, fault right-through capability, grid operation economics, voltage imbalance, load power demand, instantaneous active and reactive power, grid connected and islanded mode of operation. In fact, these are the typical electrical areas where our students, our PhD, and we ourselves are working in a various aspect of, and this is all the byproducts of this renewable and storage penetration into the grid. Each one of these topics are actually the topic like PhD topic and research topic, research projects. So a lot of, you can say the possibilities are there in the these areas for working in a coming time. Renewable energy integration is one of the paradigm shift in the typical power generation and dispatch. So our classical way of generating the power was you forecast the load and generator fleet has to follow the load through its typical regional load dispatch centers. This is the common way of generation of power, that you forecast the loads and the load dispatch center give the references to the various generating companies to ramp up their generators for delivering the power. But with the development of renewable and storage, there will be a new way of dispatch of the power, that you forecast the load as well as forecast the renewable. Because now renewable is also under the forecast condition. It's not like a fully controllable source. And then you find out the net load requirement. That is load minus renewable. This is the net load. And then the conventional generation will follow the net load. So this is the new term, net load. What is net load? Net load is load, typical load minus the renewable. Because most of the renewables are there in a distribution system. And how we connect renewable to our distribution system? For example, if you are in an institution, you have a solar rooftop plant. Let's say you have 1.5, 2 megawatt of a load, and you have a 1.5 megawatt, 1 megawatt of solar plant. So approximately it is having a capability to generate 600 kilowatt of renewable energy. So what you can do, you can subtract 1.5 megawatt, I mean 0.8 megawatt from 1.5 megawatt, and 0.7 megawatt is your requirement. So now that has to fetch from the grid. So this is what the new trend has to follow, because earlier our generation, transmission, distribution, these was the three categories of power system. Now generation has penetrated into the distribution. Now we no longer have this demarcation of generation, transmission, distribution, because distribution itself has a generation through renewable. So, and now it is coming in the range of 25 to 50%. So no longer is the generation is at a remote location. Generation is there on our rooftop or next to our house. We have a solar plant is a generation. So very typical things is supposed to, a power system is now have to be renovated with a new classical control ways, and storage and distributed generation. These are the two things which is going to play a major role in this newer paradigm shift of operation. A power system has to become a flexible, like a smart power system, microgrid, nanogrid. These are the new terminologies which is supposed to play one of the major role. Okay, so typically coming to the storage, uh, we call it electrical energy storage. Storage means general storage, but when we are talking about electrical energy storage. Uh, Due to higher round trip efficiency, the EES is potential solution. That's what I was talking about. Round trip efficiency, energy required is the ratio of energy delivered to the energy required to store the same amount. That's the round trip efficiency. So electrical energy storage has a higher round trip efficiency, unlike mechanical, like flywheel, pumped storage. They have a very less round trip efficiency. Let's say 20 to 30%, let's say the round trip efficiency of a typical flywheel, and we have about 70 to 80% efficiency of electrical energy storage. So definitely we are better off with a electrochemical energy storage. But if you come to typical electrical energy storage like supercapacitor and electromagnetic coils, the round trip efficiency is about 95%. So that's going to play one of the major role in the terms of storage. State of charge is an important control parameter, as we all understand. Bidirectional DC to DC converter along with energy management, supervisory control play a vital role, right? So you can see typically the importance of storage. You can see the solar profile over a day, 0 to 24 hours. You can see how the solar is variable, how intermittent and how random these type of renewables. This is typically solar. This is typically a wind over a year, over a day, over a month. You can just check how intermittent is this wind supply. Now, this is all the kind of the uncontrolled resources, and how we can actually need to be conditioned and need to levelized. So who will levelize it? Who will levelize? You can see this diagram. This is a typical generation through renewable. Let's say we have one side load, we have one side, other side renewable. This is the power electronics processor, power converter. So how to levelize this? You can see, suppose this is renewable, you can say it is like a random nature, right? But you need on the other side load as a constant power. So how to levelize it? How to levelize it? By using a storage. See the storage. So ultimately, this is a power processor. This is a power electronics processor, which is levelizing the randomness in the renewable. And that's how the energy storage is going to play one of the major role. To make a PA equal to PV, to make a PA equal to PV, you need a storage. Otherwise, PA is not equal to PV. Right? If you remove this, this is the power which you are going to feed to the load. And that is definitely not a kind of power we want. So one of the reason I would like to emphasize here, one of the reason that renewable storage have become so popular nowadays, is because of the development of power electronics technology. Is the development of power electronics technology. Without power electronics, you cannot think of renewable and storage. Remember that. Without, you go down the line 20 to 30 years back. Okay? Not going far away, you are sitting in your home and you have your home inverter next to you, right? Remember about 30 years back when we used to have UPS and inverters, they were so unreliable because we were not having a switches like reliable switches like IGBT and MOSFET, which we are having today. Those times, I still remember when I bought first inverter in my house, it was power transistor based inverter. And what was the problem with those? Those were, I mean, every uh, few months, those switches are going to burn out because they were not so compact and so seamless operation like we have switches like IGBT and MOSFET these days. And tomorrow we have another set of switches like silicon carbide and other technologies. So these are the power of these power electronics. How they made so significant contribution in the power conditioning, and that's how we are talking about all these resources. Otherwise, they are useless. Just think of, you have a solar panel and I give you a fan. You have a solar panel and you have a fan. You can definitely operate that solar. You can operate your fan with the solar. But think of when you need it most, it won't operate because there may be some time solar, sometime it is not there. Right. So ultimately, you need a power to be conditioned from these renewable, and storage is going to. That's what is all. Now, what are the other aspects about the energy storage? Variation in energy demand. That's what we call load leveling. Variation in energy supply, interruptions in energy supply, transmission congestion, demand for portable energy, efficiency of energy system, energy recovery. So next generation smart grid without storage is like computer without hard drive. Now this is a kind of a thing. Energy, I mean smart grid without storage is like a computer without hard drive. So important, somebody told. So think of this line and it will go into one of the major things. So now you can see here, suppose you have a solar, which is a typical this profile, Gaussian profile, and you have a requirement of your energy in your home like this, right? Now, how to fulfill this? That's what the storage is going to play. The storage will level out these variations, and that's what it's all about. Now, what are the other value addition from solar? Increase renewable energy integration, reduce dependency on fossil fuel, reduce operating expenses, balance electricity supply and demand, improve power quality and reliability, avoid costly system upgrades, keep critical equipment online during power disruption, reduce utility bills and generate revenue, reliable backup power during severe weather, reduce utility bills and generate revenue. So these are the so many value additions. Where the storage can be used, it can be used in utilities, grid operation, commercial consumers, residential consumers. So much of high segment of utilization of storage. And you can just see where the ESS find its place in a typical generation, transmission, distribution. Everywhere it can be have a value, right? So even in generation, you need storage, maybe in some other form. You go to typical thermal power generation, you will find significant storage. May not be like a load leveling, but for some purpose, right? Similarly, you go to your house, you have a battery storage in your inverters. You have a suppose a solar PV plant or a renewable plant. You need the storage for bidirectional power flow. So everywhere you need a storage for various purposes. Now, as far as new term, which we call grid scale storage, this is a new terminology. Grid scale or utility scale storage, right? This is different from our typical battery, which we are using in our house, in our UPS, or somewhere. It is a storage which is like a substation. Now the concept of storage is coming like a substation, right? You have a very big space where you have a typical storage. So total Grid is utility market is expected to touch total storage capacity of 2,500 gigawatt hour, including the storage in electric vehicle batteries and pumped hydro. The considerable increase in stationary storage, also called battery-based storage, tend to increase for utility applications, right? And 2030 major shift in PV plus storage to between 110 gigawatt hour to 160 gigawatt hour. So this is what, and about 70 gigawatt hour to 90 gigawatt hour produced by the India. As far as grid scale storage, we have some pilot projects like in Delhi, we have about 250 kilowatt hour installed in 2019 by Delhi Distribution Limited, right, with some Mitsubishi Corporation. NTPC has floated tender for 1,000 megawatt hour in 2021 last year March, although it could not be materialized. So right now, lithium ion batteries are playing a major role in grid scale storage, and it will continue to play a major role by this decade as well, because that's the one of the portable storage and very have a potential of high capacity storage. Now, let me just have a brief about the storage. We have mechanical, electrochemical, electrical. These are some of the standard storage technology, like mechanical. Pumped hydro is one of the major storage nowadays. We are using compressed air. We compressed in a tube-like structure, and then we release to run the turbines. Flywheels is a very typical way of storing in a rotating wheels, and one of the major workforce of storage in a thermal power generations in some of the applications. Electrochemical, like secondary batteries, lead acid, nickel, cadmium, nickel metal hydroxide, lithium ion, sodium sulfate, and then just I was mentioning, lithium iron phosphate is one of the upcoming secondary storage batteries, which is very useful for a utility scale. Flow batteries, like a tank storage batteries, where you have a big tank for electrolyte, and it's also upcoming for a medium scale application, redox flow and hybrid flow. So these are the electrochemical. Then we have a purely electrical, like supercapacitor or ultra capacitor, electrical double layer pseudo capacitor, hybrid capacitor. These are the form of ultra capacitors which are used for applications. Superconducting magnetic coils, as I just mentioned, it's another electrical way of. So this is the electrostatic way of storing the energy, and this is the electromagnetic way of storing the energy. So typically we use capacitor and inductor as we call storage devices, but at a very small level or a transient levels. But if we want to go for a steady state levels, then we have a supercapacitor and superconducting magnetic coil as a replacement of capacitor and inductor. You can see some of the pictures I have taken from different resources. Actual plant level storage pictures, pumped hydro storage, like a typical dam. It's a pumped hydro storage. You can see the flywheel, right? This is a compressed air. So this is the plant level pictures of these storage. Electrochemical, when it comes to utility scale, electrochemical storage, you can see secondary batteries, lithium ion batteries, right? Lead acid batteries at a plant level. Other form of, this is the flow battery, you can see. Typical pictures are very nice to see all these pictures. Okay, then electrical, when it comes to purely electrical, We have certain like supercapacitor plant. You can see it's not a single capacitor, it's a bunch of capacitor banks of supercapacitors. You can see this superconducting magnetic coil, such a huge magnetic coil, which can be used for storing the in a form of a magnetic energy. Then we have another set of upcoming storage. Those are like fuel cells, hydrogen fuel cells, which is so popular nowadays. So many people are working. Right? So you can see that heat storage, another form of storing the energy in a form of heat. So many plant level, I mean, the utility scale storage. We have seen all these things in a very lab level or in a house level, but these things will be coming in a plant level, and then only we will be able to say 27 gigawatt of storage. How it will come 27 gigawatt of storage by end of this decade? This is the pictures you will be seeing in a coming future. All of you working in the area of this electrical and chemical and all those things. Anyway, this is the very typical table. You can find it on the internet also. The comparison of various forms of energy, right? So you can see what are the storage which we can compare. We can compare on the parameter. I mean, ultra capacitor, supermagnetic coil. These are the secondary batteries: lead acid, lithium ion, nickel metal hydroxide, flywheel, pump storage, and compressed air. And these are the two very useful parameter. One is called we in a short we call power density, and other we call energy density. Here it is written specific power watt per kg, specific energy watt hour per kg. So this is power density and this is energy density. Very useful parameter for comparing the various energy storage. We have a life cycle. Any storage, how we measure its life by how many cycles it go through charging and discharging, right? So these three are very useful parameters. And then third very useful parameter is efficiency, round trip efficiency. What is the round trip efficiency of a storage? And then self discharge. Self discharge means if you are not using, how much time it will take to discharge, okay, without even using. That is also one of the parameters. Okay, right. So these are the typical applications. I'm not much focusing on all this, but these are typical application. But what are the important things I would just highlight? Ultra capacitor and super magnetic energy has a very high power density. Remember, these two purely electrical energy has a very high power density, but their energy density is very, very low. And that is why they are not usable for your laptop, for your mobiles, for your inverters. They cannot be used for such applications because of their very low energy density. You need larger amount of power over a longer period of time. And that is what the one most unfortunate part for our electrical people. And there we are lacking. We don't have a compatible purely electrical energy storage. And you look at the efficiency, more than 90% efficiency. The highest efficiency you have with the supercapacitor or ultra capacitor. But unfortunately, they are not of much use because of their very, very low energy density. Okay, they can be useful for transient supply of power like driving electric motors, electric vehicles, running your, solving your power quality problems. Okay, short-term supply of power, for them it is very, very useful. But they are almost useless as far as energy storing capacities are concerned. So what is more useful in such situation? These secondary batteries, which are electrochemical, right? Now, electrochemical has a very good energy density. You can see here, and that is why they are useful for almost everywhere right now. Right from starting from milliwatt hour of your mobile phones to megawatt hours in power plants. They are being used, and that's what we are talking about. Lithium ion battery, lithium iron phosphate. These are the newer series of secondary battery, but they are electrochemical. That means if dynamic performance is concerned, on electrical side it's very good, but on the chemical side they are based on the chemical. So as far as dynamic performance is concerned, it is only the electrical sources of energy like supercapacitor of magnetic energy resources which can provide a very good support as far as dynamics is concerned. Purely mechanical, they are very good. They are very good, both energy and power density. But then the problem is they are very poor dynamic performance, and they are very poor energy efficiency. So these are the reasons that we are still sticking on these middle level storage, and that's what we want actually. You will be taught by many other speakers. I should not spend another set of time on this. Let me come to some other. This is another view how you can see typical battery energy storage. Typical, if you go to any solar standalone solar PV system in your lab, you will see these are the things. You will be having an inverter, big inverters. You will be seeing a battery system, battery banks, right? You have a energy management system, which is mostly in the form of softwares installed on your computers. So you have modules, cells, so many other data acquisition devices, container, temporary building. So it all depends upon what type of application you are going through. This is one of the picture which is shared by one of the company to me, that how storage is going to be used for a grid scale utility application. So you can see the racks of batteries, megawatt hour batteries you can see here. Battery racks are there. Then you have stacks, filter, circuit breaker, various levels, all these. Okay. Then you have a transformer. You have a transformer fitted by so many sites, and then finally to the grid. Uh, Support from typical utility scale battery storage connected to 33 kV bus. So this is how the utility scale batteries can work in the future. We have to see what are other possibilities. So power conditioning system. This is typically a power electronics converters, which may be useful for storage, charging and discharging of the batteries. Now, as I already mentioned, what are the needs for power electronics converter? Efficient interfacing of energy storage, efficient charging and discharging, uh, protection, bidirectional power flow, converting voltage in appropriate format, uh, MPP operation, maximum power point operation, AC grid and DC bus interface, bidirectional AC to DC converter. So typically now I'm little bit coming to the power electronics to give you some glimpse. This is how the power electronics can play a role in a typical microgrid situation. We have, let's say, energy storage. You can see this is a rack of energy storage. We have a power electronics interface. We have a electric grid, a power electronics interface. We have a fuel cell, micro turbine, PV module, wind turbine, power electronics interface, and all of them are coming together to form a microgrid, which feeds to AC load, DC load through respective power electronics interface. So you can think of a smart grid which is surrounded by so many equipments and so many resources, and everybody through power electronics converters. So look at the importance of power electronics interface. Without power electronics interface, everything is useless. Everything has to operate in isolation. So controllers, communication, all these things have to become a kind of a controlling all these coordination and control. You can see some of the work which we have done over few years. Like this is one of the work, bidirectional power converters used for battery storage in a typical microgrid. So solar is there, wind is there. You can see typical doubly fed induction generator. You have a squirrel cage induction generator directly connected to the grid. You have a PMSG, permanent magnet synchronous generator, connected to the grid through dual stage converter AC/DC, DC/DC. And then you have a typical solar PV plant connected to the grid through DC/DC and DC/AC. And then normal power plants and the grids. So and the loads and the grids. So typical, this could be a distribution generation 11 kV bus. This could be a nature of 11 kV bus for future distribution system. That's what I was just trying to put in front of you. The bidirectional converter, as far as storage is concerned, a bidirectional converter has to play a major role, right? This is one of the projects we have done with MNRE a few years back. This hybrid AC/DC microgrid system, where we have a solar PV of about 2 kilowatt, wind power about 1.5 kilowatt, and then we developed a bidirectional converters for AC and DC loads, along with connection of the grids. So worked with actual systems. I will be showing some of the pictures. This is the schematic of such operations. So wind turbine, which we have realized through wind turbine emulator. Solar PV actual plant we have used. Battery storage we have used actual. Ultra capacitor we have used actual. And then everything through respective power electronics converter connected to the common DC bus. And then feeding to grid and a load. Low voltage distribution LVDC bus for feeding for 48 volt loads. MVDC medium voltage DC bus for feeding 380 volt loads. So this is one of the proposed structures we have done with this kind of data 1.5 kilowatt residential system. These are some of the results. Just I am scrolling through now because a lot of variation in the solar and these various levels of controls are operating, interlinking control, then current tracking at a converter level, right? Charging and discharging of the storage, which is supported by the bidirectional converters. Okay, so when the battery is there, when the grid is there, when the solar is there, so all possible scenarios we can cover. This is islanded mode. When the grid is not there, then totally the load is to be supplied either from the solar or to the battery. So what we have done, we have used current control mode operation when the in a grid connected mode and the voltage control mode in a islanded mode. That's what we have done. And these are the operation in a battery operation under the islanded mode of operation. This is another project we have done in the past. Bidirectional DC-DC converter we have proposed with a battery and then unidirectional power flow from solar to grid load, local load. This is the islanded mode of operation. Sorry, this is the standalone mode of operation. Isolated DC microgrid system. These were some data. 2 kilowatt system again. used for operation of this standalone PV system. The standalone PV system and DC microgrid. That was the combination. Charging and discharging of the battery during different operating hours. Various modes of operations. Bidirectional converter used in a buck mode and boost mode for charging and discharging respectively. This is just one look of the same thing which I was just talking about. And we have used some time back this setup for this hybrid AC-DC microgrid system. This is another project we worked 2 years back, just before Corona, with a solid state transformer using parallel dual active bridge. So this is one of the very interesting area some of you can pick up because typical transformer, we know electromagnetic transformer, the size of the transformer is very huge. So you can use a solid state transformer in place of typical electromagnetic transformer to reduce the size and improve the reliability of the system, and also to make it controllable transformer. Right, those are the features you can incorporate in us. And this also uses a bidirectional power flow and storage. You can see here the typical structure, which we also worked. Three-phase AC grid in this side, AC bus on other side with loads. Then we have you can see DC bus supported by DC microgrid, and then we have used dual active bridge, AC grid to AC microgrid, DC microgrid, solid state transformer. So this is another area of interest if you are using even the storage also, very useful. This is work which we work with a solid state transformer, parallel DAB, for transfer of power from multiple grids to a common grid. That's how we have used parallel dual active bridge, which is collecting the power from multiple grids and transferring power to a output side so as to improve the reliability and high power transfer capability. That's what very interesting work. This is a setup which we have used with, I think, with multiple resources power transfer, solid state transformer. Okay, so I hope I should close it now. We are close to the timing and we keep some time for discussions. So that's what the end of my slides. Challenge and the participant.
Yes, sir.
Okay, so do you want to continue with some of more slides, or shall I stop here? It all depends upon you. I can continue with something else also. Not a problem if it is a time crunch situation, or if somebody want to enter into discussions, we can have more discussions. That may be more useful.
The participants can interact with our expert. So if anyone is having any query, he can ask. Any participant.
Hello.
Please go ahead.
Sir, good evening, sir. My name is Banath Somarna.
Yeah.
Sir, actually, in DC microgrid and AC microgrid, when we are constructing the hybrid microgrid, both of them. So, if can fault detect, sir, we can detect the fault. Means
Yeah,
AC
this
to
is
DC power conversion management
yes.
system.
Actually, this is a very interesting area, which even we also thought of working because protection schemes are very new for hybrid microgrid or even for a renewable based microgrid or a smart grids. So detecting a fault in situations, actually there are a lot of categorization of faults. And the size of system is so variable that I still doubt that there is a standards for fault detection. But detection of fault is definitely possible. And because there are so many types of fault actually.
Okay.
And it's really, I mean, if you go to the renewable side, solar
Yes,
PV, there are so many possibilities of fault on a solar site. There are so many possibilities of fault on a DC site at a low battery site and on the DC load site. They are different actually. Then we have a different fault conditions on a AC side also. So many variations are there that even in my institute also, in my group, they have written a project and they got it also. And we are working a fault detection in a hybrid AC-DC microgrid system. So true, it is possible, but it is challenging actually. We can't comment much on this because still we are, I mean, there is a development and standardization of the faults at this level.
Okay. Thank you, sir.
Yeah.
Any other participant?
Yeah. I was just trying to open up something else in case. Yeah, this is one of the work with the bidirectional converter. Yeah, that's very interesting actually for storage purpose. I mean, one of the PPT I prepared some time back for storage with a bidirectional converter, because storage as a phone is largely the performance of the storage, especially in a high power application, largely depends upon this converter of performance. And dual active bridge, because I did talk here, one of the important role which is going to play is a DAB, dual active bridge. You can see here, yeah, this is exactly this. I hope many of you are working on the dual active bridge converter, and this is one of the major converter which will be used for high power transfer, and that's how we can incorporate. I'm just showing some of the picture with regard to storage and dual active bridge. So this you can see. This is one of the pictures. I hope this is visible. Dr. Sanjeev, is it visible?
Yes, sir. It is visible.
Okay. Yeah. So this is, you can see the structure of dual active bridge, which is actually an isolated converter, which is transferring power from renewable to storage in both the direction, means charging and discharging. So this is one of the efficient way of storing the power, and this is what the performance of this dual active bridge. And you can see in so many ways this dual active bridge can be used. Like this is a parallel connection of dual active bridge with the storage. So if you have a very large amount of power, you can you can transfer from HVDC link even to the storage in this way by paralleling of dual electric bridge. You can see there are so many possibilities: series, parallel, 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 parallel series, right? So I was just giving you, and then we also had some interest earlier with a multi-port uh, uh, transfer of the power. I mean, you have a multiple ports on a common bus, and then you have a possibility of power transfer. Suppose this is TAB, 3-port bidirectional DC-DC converter. So power can be transferred from this end to this end, this end to this end, and this end to this. I mean, LV to LV also, inter power transfer is possible. And therefore, you can have even the multiple option of LV bridges or LV-HV combination bridges. You can see on the top also, there are 2 LV bridges which are connected. So, yeah, this is typical implementation we have done in labs also. The storage of the power and transferring of the power from one end to other end. And then I will be showing one interesting topology. Yeah, integration of multiple bridges like this one with a storage. This is a parallel multi-input dual electric bridge. We call multi-input dual electric bridge to transfer the power to the DC bus from the multiple resources. And then this is one of the very important topology which we have proposed: multi-input configuration of dual electric bridge. So if you have multiple storage, you can actually choose any storage at any point of time. So that's what one of the proposal we have done about 4 or 5 years back. And this is how it can work. And then this is again the multiple. So I just in the middle, I just thought, let me share some of the more slides to give some information to the participants. So that's all from my side. Thank you. If any other question from anybody.